having me here to present my work. I'm Chun-Hao. I'm a graduate student from Stanford. So today I'm going to talk about the conditional luminosity function of ray galaxy in massive clusters. So this is a work in collaboration with Eduardo Razo, Eric Kov, and my advisor, Risa Weiser. Okay, so first, a bit of motivation. I think this plot has been shown like many times in this conference. So let me just remind you. So this is a plot from Peter Bertuzzi's universe machine paper, where he plotted the cell mass-Hell mass relation as a function of peak Hell mass. So as pointed out in, I think it's in Song Huang's talk on Monday, that the uncertainty at the high mass end is still very significant. So in this work, we are the main motivation for this work is trying to shed light on not only the mean relation of the cell mass-Hell mass relation, but also the scalar. Right. So the approach we take is we have optical identified cluster sample, and then we measure. So currently we focus on the luminosity, but in the future we will extend this work to a cell mass. So we measure luminosity function. And then we have a Ford model to connect the whole cell mass to the luminosity. Okay, so this is the outline of the talk. I'll briefly describe the samples, the measurement and modeling, and also tell you some implication. Okay, so the sample we use, I think it's already mentioned in Susmita's talk yesterday. We are using the RainMapper cluster finder. So how RainMapper did is looks for clusters on the optical image. It identifies clusters as a group of ray galaxies. This algorithm, they use all the member galaxies to determine the redshift of the galaxy cluster. Right, so here I'm showing you the y-axis is the spectroscopic cluster redshift as a function of the redshift reported by RainMapper algorithm. So you can see they line up each other pretty well. We reached the redshift uncertainty about about 1%, 1 to 1.5%. Right. The second good thing about this cluster finder is it has a well-calibrated mass tracer called the richness. Essentially, the richness is the effective number of ray cluster members with luminosity greater than 0.2 L star. Right, and another good thing, like why this sample is very good to for our science, is that it has a well understood membership probability. Right. So here I'm plotting the membership probability reported by RainMapper and the spectroscopy identified cluster members. So you can see the membership probability line out with what you expect from spectroscopy sample pretty well. The central galaxy is one of the hardest things to define in the real data. So the nice thing about RainMapper center is the centers in the RainMapper is not only the BCG in the cluster. This is a combination of the luminosity and color cut as well as the position of the galaxy in the cluster. So it provides you like 5 most probable centers candidates with centering probability. The samples in this talk is mainly focused on the SDSS DRA catalog. We have a cluster range, have like 1/4 of the sky, ranging from redshift 0.1 to 0.3. In total, we have 7,000 galaxy clusters that's been identified with mean mass about 2 × 10 to the 14 edge-inverse solar mass. Okay. So the procedure we take is that we measure luminosity function as a in bins of richness and redshift, and then we connect the richness to the mass by adopting some richness mass relation that is analyzed in Constanzi et al.'s paper. Basically, they analyze a combination of the cluster number counts and also the weak density measurements. And then we forward model the galaxy properties, basically the luminosity function and the richness as a function of whole cell mass. Okay, so this is our measurement. I showed you 9 bins. So this is like from the left to the right is increasing in the redshift from the top to the bottom is increase in the richness, basically essentially increase in the mass. For each panel, this is luminosity function we measured. I'll describe this in detail later. But I just want to remind you, even I show you like 9 panels here, we actually have 5 richness bins and 4 redshift bins. So we have in total 20 bins. And on top of these data points, the red line is our model. So we have a single model that can describe these 20 bins of luminosity function pretty well. Okay, so I promise you I'll go to some detail about luminosity function. So the y-axis, so this is a zoom in for a panel here. So this is the y-axis is the galaxy number density as a function of galaxy luminosity, right? Okay, so the first thing you will notice is this this triangle line here. This is the satellite luminosity. So we modeled it as just a straight function with free broad slope and the flat slope. The circle here I'm showing as the luminosity function for the central galaxy that is identified in RedMapper. So we modeled it somehow different than like other people's work, which is we model the luminosity and the richness at a fixed Hale mass jointly. So we are not just using the single log normal distribution, we actually model it as a multivariate log normal distribution. Right, so for a satellite and the central model, like in all the conditional luminosity function, you have some parameter that depends on the host Hale mass, right? So these 3 parameters are dependence of the host Hale mass. And we have other parameter that is just modeled as a constant, namely the blind slope and the scatter. One thing I want to highlight is we introduced this new parameter. This is R, which describes the correlation coefficient between the richness and the central galaxy luminosity at a fixed Hale mass. Okay, so the key ingredient of this model is here we introduce this R. This is correlation coefficient between the central galaxy luminosity and the richness at a fixed Hale mass. And right, I'll skip the second point. The third point is in this work, we fully marginalize over the uncertainty in the richness mass relation. So our error budget is very conservative. This is the result. Right, so for the central model, so we have 4 parameters. The first is the scatter, like which a lot of people care about it. The second one is this new parameter we introduced in this work. The third and the first one are the description of the luminosity and the Hale mass relation, right? So the normalization and the slope. Okay, I'll zoom in the top panel. So yeah, so it's this panel. Right, so what we find here is that we find that this R is positive by many sigma. So what we find is that at a fixed Hale mass, the richer clusters tend to hold brighter central galaxies. This parameter was implicitly assumed 0 in most of the conditional luminosity functions work. And the second thing we find is the fact that this R is positive, it drives our scatter to a larger value. Right? So you might want to ask, how is our best fit scatter fit in the model that we have? That is this in the literature. Right, so this is a nice plot by my advisor, Risa Westers, in her review paper this year. So where he plotted is a bunch of scatter as a function of host Hale mass for both the hydro simulation model and the empirical model. So you can see, since the model forms into different groups, one group prefer a higher value of scatter, one group prefer a very low, smaller value. This result is what we find in this work, right? So with the uncertainty here. So our work preferred a larger value for the scatter. Right, and then here I'm showing the luminosity mass relation we have for both the central galaxy and the satellites. Okay, so you might want to ask how is our work compared to other people's work? Here I'm showing you a comparison between Hansen et al., which is the similar cluster sample within a similar redshift range and mesh range. You can see our result lie pretty much within 1 sigma. So the result, though, we prefer a slightly smaller value. I think it's because how they do this, how they connect the mesh to the luminosity is that implicitly assume this ought to be 0. And for the satellites, something interesting is that we find the satellite luminosity is actually does not depend on the host Hale mass. It's quite surprising for us. The blue line is a comparison with Young et al. Satellites. You can see the slope is steeper than ours. Right. Okay, so almost the last slide. Right. So this is then you might ask like, how is our work compared to the approximation work, right? So you might ask like this flatness because it's due to some like selection effect in the cluster finder. So we actually did a luminosity approximation with the scatter that is preferred in this model. So the straight line corresponds to 3 scatter. Like this is the most probable value, and below 1 sigma and above 1 sigma. So you can see our luminosity mesh relation actually mesh this approximation work pretty well. For a satellite, I won't pay a lot of potential of this normalization because this correspond to some luminosity cut we choose. But the fact that the approximation also prefer a flatter correlation is similar to what we found. So this is the conclusion. I'll take questions right now.
So there has been a lot of literature recently on projection effects in RedMapper. And I mean, do you have any feeling for whether this will affect your results or not?
Right, so I think the projection effect mainly affect the richness mass relation. And in our rich mass relation model, we already include those effects. So we fully marginalize over the projection effect in our analysis. So I don't think that would possibly affect our results. The one thing I want to point out is additional, not the projection effect, but similar thing is the miscentering thing, right? So we actually, so as you can see in these plots, we actually have considered many different systematic. Include the breakpoint actually also consider this miscentering effect.
Okay, more questions?
Are you able to explore the changes in the luminosity function as a function of the radius away from the center of the galaxy? Obviously, you don't have the central galaxies there, but how much does the luminosity function vary as you go from the inner to the outer regions of these clusters? Do you have a handle on that?
We haven't looked at that.
Is that worth looking at?
Yeah, I think the Hansen et al. They actually look at the like 2009 paper. They actually look at the luminosity as a function of radius. It makes BCG catalog. In principle, we can also do the same analysis. But in this work, as a first work to look at the luminosity distribution, we haven't done that analysis yet. Yeah, we have all the data today. So in principle, we can do it.
Okay, do we have more questions? No. Okay, let's thank the speaker again.